This is week 12 and the last week on this upper thermodynamics course. So this week session consists on reciprocating compressors. So we look at compressors in general and multi-stage compressors and the processes, how to calculate those and the efficiencies of compressor, volumetric efficiency and so on. So now this week is just the component which we are looking at, the compressor. So till now we covered the cycles, how to do that. So the compressor is one of the major component which is being used in the cycles. So with that we'll start. So this week's have similarly prepared MCQs and some numerical problems on compressors. So we'll see those. To start with, the first question is: rotary air compressors are suitable for dash. A. Higher discharge at higher pressure. B. Low discharge at high pressure. C. Higher discharge at low pressure. And D. Low discharge at low pressure. So to start with, compressors can differentiate in two types. One is reciprocating and one is rotary. In this we have already discussed in the IC engine part. So we'll come back again. We have reciprocating and well as rotary. The major difference is in reciprocating type you don't have continuous flow, but there are flows which is happening intermittently. In rotary you have a continuous flow. So that is the major difference which you can see. So with that, reciprocating is used for higher discharge, higher pressure ratios. So rotary compressor is used for higher discharge at low pressures. So reciprocating is used for a higher pressure. Here it's if you have flow rate is more, or your requirement for so suppose you have to put up an air conditioner or in a mall or a airport for example. So there the requirement for cooling is very high, so you need a bigger plant. So where you need a more mass flow rate, in that case you go for a rotary air compressor. So where the discharge requirement is higher, so hence option is C, higher discharge at low pressure. Next is reciprocating air compressor, displacement machine. So these are all positive displacement machines. So reciprocating, so you have there is your scroll compressor or screw compressor, or these are all positive displacement compressor. So you are efficiently reducing your volume. So there are positive displacement types. So reciprocating air compressor is a positive displacement type machine. So the answer is true. So next is, in an ideal reciprocating air compressor, the work input will be minimum if the compression follows a dash: A. Reversible adiabatic process, B. Isobaric process, C. Adiabatic process, and D. Isothermal process. So you are doing a compression process by 4 processes shown listed. So which will have the minimum work requirement for the compression? That's what is being asked. So suppose you have pressure P1 and suppose assuming 1 and you're compressing it to suppose 6 bar. So which process will give you lower work input? So for this case the answer is D, isothermal process. So out of the 4, if you evaluate the work for all of these 4, so individual PdV, so you will find that the isothermal process will take the least amount of work. next is for reciprocating compressor, as the value of pressure ratio increases, the volumetric efficiency dash A increase, B decreases, C remains constant, and D none of the above. So if your pressure ratio increases, what happens to the volumetric efficiency? That's what is being asked. So these two, if you remember, we have discussed when we were discussing about volumetric efficiency. So volumetric efficiency can be defined in terms of your swept volume and the pressure ratios. Swept volume by clearance volume by swept volume. So 1 minus C into 1 plus R raised to power 1 by gamma. So we have pressure ratio there. So what exactly physically we see what happens. So volumetric efficiency, your piston goes up and down, so it sweeps some volume. So ideally that is the volume which the compressor should push, and the mass flow rate will be to that volume. Ideally that should be the mass flow rate flowing across the compressor which you are compressing, but that doesn't happen because when we saw there is always a need for clearance, or else the piston will go and hit the top portion, and also you need a compression. You are compressing, you cannot fully compress and compress it to a volume of 0, that cannot happen. So there will be some always a clearance volume at the top, so you will compress to till that portion, and when the valve opens, discharge valve opens, so your inlet pressure inside the compressor is more than the discharge side, so you will push the valve and the flow will occur, and the gas will escape from the compressing cylinder chamber, compression chamber, and the pressure inside will reduce and the valve close. So all the gases will not escape. So there will be some amount of gas which will be present inside your piston cylinder. So when the piston again moves down, when the suction stroke happens, so the initial pressure gas which is in there, which has not left from the cylinder, so that will expand, and once it reduces to a pressure lower than your suction pressure, then your suction valve will open, and the air or fluid will come inside. So till that portion there is no intake, so that is amounting to a waste, so that will reduce your volumetric efficiency. So if you are having higher pressure ratio, so this region where you have to expand will increase, and this will keep on reducing your volumetric efficiency. So the answer is option B, decreases. So if your pressure ratio increases, so as I told, the amount of length the piston has to reduce for the suction valve to open physically, so that will increase. So that increase will effectively reduce your volume which is there for suction to happen or the new fluid to come in. So that will reduce your volumetric efficiency. So answer is option B, decreases. So next is, in perfect intercooling arrangement in a reciprocating compressor, it is possible to achieve the isothermal compression with minimal work input. So in perfect intercooling arrangement in a reciprocating compressor, so I saying you have you can achieve isothermal compression by doing a perfect intercooling, and which we have already seen. Isothermal will give you the minimal work. So answer is true. So what basically is there, you need a multiple intercooling stages. So you compress it a little, then you let the gas come to the initial suction temperature by intercooling, and then compress, and then you do this process repeatedly. Then what is you will try to push the process towards an isothermal process. So it will not be exactly an isothermal, but you are trying to mimic an isothermal process. So but you have to do a series of steps, and this will be slower. So answer is true. Next is, in a two-stage reciprocating air compressor, with a suction pressure of 4 bar and delivery pressure of 16 bar, the ideal pressure for intercooling will be, so now we have a two-stage compression. So we are using an intercooler in between, two-stage compression. You have to compress from 4 to 16 bar. So what is the ideal pressure for intercooling to happen? So this we'll see. So you will get it come as root of P1 into P2. This comes from minimizing the total work. So you are compressing from 4 bar to some intermediate pressure P, and then you are compressing from P to 16 bar. So if you add these two work, that will be the total work which you have to supply for this compression process. So if you try to minimize this work, if you differentiate it with respect to the intermediate pressure P, then ultimately what you will get is, so this dou W by dou P is equal to 0. So if you solve this, you will get the intermediate pressure P as root of P1 into P2. That gives you root of 4 into 16, that is 8 bar. So this is the ideal pressure for intercooling, which will give you the minimum work. So answer is 8 bar. So next is the ratio of the volume of free air delivery per stroke to the swept volume of the piston is known as dash. A. Isothermal efficiency, B. Isentropic efficiency, C. Adiabatic efficiency, and D. Volumetric efficiency. So last, the ratio of the volume of free air delivery per stroke to the swept volume. So that is basically what we saw previously. What amount of volume flow rate is happening compared to the swept volume. So this is given by the volumetric efficiency. So answer is option D, volumetric efficiency. So the next question is, an air compressor receives in air, so R value, gas constant value is given for air is 0.287 kilojoule per kg Kelvin. So this air is coming into the air compressor at 1 bar and 20 degrees Celsius and compresses it according to law PV raised to power 1.2 equals constant. It delivers the air to a receiver at a constant pressure of 10 bar. So that means your discharge pressure is at 10 bar. So the compressor is delivering it to that pressure vessel which is at 10 bar. So you have to compress it to that bar so that flow can happen. So your discharge pressure is 10 bar. So the temperature of air at the end of compression is dash. So this is a polytropic process. So we'll see how to solve this. So PV raised to power gamma is equals constant, PV raised to 1 by 2 is equals to PV raised to power n is constant. So temperature at the end of compression is given by T2 by T1 equals P2 by P1 raised to power n minus 1 by n. So this you can substitute the ideal gas equation in PV raised to power n equals constant. So if you substitute volume terms in terms of pressure and temperature, so this is what you will get, T2 by T1 equals P2 by P1 raised to power n minus 1 by n. So substituting the initial and final pressure, so P2 is 10 bar and P1 is 1 bar and n is given as 1.2. So substituting we will get the ratio of temperature is 1.468. So the outlet temperature is 1.468 times the inlet temperature, which comes out to be 430 Kelvin or 157 degrees Celsius. So similar to the previous question, we need the same question, process, but this time we need to find out the work done during compression. So previous question we were asked to find out the temperature. Now we need to find out the work done. So similarly, the work done will integrate PV raised to power n equals constant, that is a process. So P dV, so substituting pressure in terms of volume and integrating it, and then substituting back in terms of pressure and temperature with ideal gas equation, you will get your work done as mRT1 into n by n minus 1 e times your pressure ratio raised to power n minus 1 by n minus 1. So this is your work done, the equation for work done. So substituting the values here, so R we are mass we are assuming per kg of air, R is 0.287 and inlet temperature is 20 degrees Celsius. So 20 plus 273 gives you 293. So that is the inlet temperature in Kelvin into your polytropic index. This is 1.2, and then pressure is same. Final pressure is 10. Initial pressure is 1. So substituting this, you will get your work done for the compression process as 236.13 kilojoule per kg of air. So next question is, a multi-stage compressor incorporates 3 number of stages with perfect intercooling between the stages. The compressor receives air at pressure 1 bar and delivers the compressed air at pressure 8 bar. For a minimum indicated power requirement, the pressure ratio for each stage is. So now instead of 1, we are doing it 3 stages. So you're compressing from 1 to 2, and then 2 to 3, and then 3 to 4. So you have 3 compressors used to compress from 1 bar to 8 bar. So we need to find out for having a minimum indicated power, so that is the total work done is minimum, what should be the pressure ratio of each of the stages. So just like what we saw previously, for 2 stages it was P2 into P1 raised to power half. So here the individual stages was raised to power half. So here it will be 1 by number of stages. So that will give you the minimum indicated power. So the pressure requirement is for each of the stages is P2 by P1 raised to power 1 by n. So that is 2 bar. So the pressure ratio is 2 bar or 2. So with that I have finished all the MCQs. So now we'll move on to some numericals. So first one is 1 meter cube of a gas is compressed adiabatically, for which gamma value is 1.4, from 1 bar to 5 bar in a reciprocating compressor with 8% clearance if the exponent of the re-expansion curve is 1.1 instead of 1.4. Find the percentage increase in the work of compression. So what is given is, you have 1 meter of gas which is compressed adiabatically, so gamma value is given, from 1 bar to 5 bar in a reciprocating compressor, so which has 8% clearance volume. If the exponent of re-expansion is 1.1 instead of 1.4, find the percentage increase in the work of compression. So this is similar to the process which I explained. So your inlet is at 1, so from 1 you are compressing it to 2, then you have your pressure, your gas is going out to the discharge, and then again the piston is moving down in suction stroke, during which the gas which is entrapped is getting expanded, so from 3 to 4, and then 4 is your suction pressure where your gas is coming in. So 4 to 1 is your where your gas is coming in. So this is the process, actual compression process. So for this Now for adiabatic compression and expansion, first we will assume an adiabatic compression process. What is the work done? So for adiabatic work, W is gamma by gamma minus 1 into PV P1 V1 into P2 by P1 raised per gamma minus 1 by gamma minus 1. So substituting the values here, so 1.4 divided by 1.4 minus 1 into your inlet pressure is 1 bar, so 10 power 5 kilopascal into your gas compressed is 1 meter cube, so V is 1 into your pressure ratio is 1 bar to 5 bar, so 5 by 1 is 5 raised by gamma minus 1 by gamma. So this comes out to be 204050 or 204.05 kilonewton meter. So that is the work which is done on the for the adiabatic compression. Then your adiabatic compression is now during the re-expansion, it is happening at 1.1. So V4 is V4 by V volume. So your P4 will be where actual expansion happens, expansion of the gas which is there. So that volume V4 is V4 by V3 equals your P2 by P1 raised to power 1 by your polytropic index, because PV raised to power n is constant. So substituting that, we can find out the volume at 4. So that volume is 0.3456 meter cube. So V1 is 1.3456 meter cube. So with this, now we can find out what is the actual work we are getting. So this is the work for adiabatic compression, and then adiabatic expansion is giving away work, so that will be reduced. So substituting, the formula will be same, just the n values will change. So substituting the pressure and volume individual values, and you will get 218.87 Newton meter. You see there is an increase in work, because previously it was compressing just 1 meter cube of air. Because of the Z expansion, that gas is entrapped in the piston cylinder arrangement, and that is increased the total volume. So the increase in work is 7.26%. So the next question is, an R22 hermetic directly coupled motor reciprocating compressor with 4% clearance is to be designed for a 7.5 ton capacity at 4 degrees Celsius evaporating and 40 degrees Celsius condensing temperatures. The compression index may be taken as 1.15. The number of cylinders may be selected as 2, and the mean piston speed as 3 meters per second approximately. The stroke to bore ratio for fluorocarbons may be taken as 0.8. Pressure drops at suction and discharge valves may be assumed as 0.2 and 0.4 bar respectively. Determine power consumption of the compressor and COP of the cycle. 2. Volumetric efficiency of the compressor. 3. Bore and stroke of the compressor. Choose motor with 1400 rpm. So if the evaporator temperature drops to -2 degrees Celsius with the condenser temperature and other conditions remaining same, what will be the capacity and power consumption of this compressor and COP of the system? So to break it down, we have a R22 compressor which has a 4% clearance volume, and it is used for a cooling application with cooling requirement of 7.5 tons. So this is the operator between 4 degrees Celsius evaporating and 40 degrees Celsius condensing temperature. So a compressed index is also given, and the mean speed is also given, and your motor speed is also given, and there is also pressure drops across the valves, which is also mentioned, and the stroke to bore ratio is given as 0.8. so we need to find out the rest. So we'll see how to solve this. So this is how the process looks. So this VCRS, which we have already seen. So evaporator, this is at 4 degrees Celsius, so that corresponds to the saturation pressure at 4, and condenser is the pressure corresponding to the saturation pressure of 40 degrees Celsius. So that is the pressure ratios, and you will have plus and minus this pressure to account for the valve drops. So that will be suction and discharge pressures. So the compressor will operate between these two pressures. So 4 degrees Celsius, your saturation pressure is 5.657 for R22, and similarly for 40 degrees Celsius, your saturation pressure is 15.335 bar, and it's given as suction valve drop is 0.2 bar. So essentially your compressor inlet is at 5.657 minus of 0.2, that gives you 5.457 bar. So this is your inlet pressure or suction pressure, and then discharge pressure is your saturation pressure plus the valve pressure drop. So in suction it's negative, you have to reduce it, and in discharge you have to add. So plus 0.5, it gives you 15.735 bar. So these are the pressure ratios, pressures in which the compressor is operating. So with this known, so if you draw the cycle in a pH chart, so 1 to 2 is your compression process, and then 2 to 3 is your condenser condensing, and 3 to 4 is your isenthalpic expansion, and then 4 to 1 is your evaporator. So using this, H1 is your saturated vapor at inlet. So at 4 degrees Celsius, your saturated vapor is 406.8, and then specific volume corresponding to this condition is 0.0431 meter cube per kg. So the enthalpy of the liquid from condenser is your saturated liquid, so that is 249.1. So with that we can find out the specific refrigerating effect, which comes out to be H3 minus H1, this is 157.7 kilojoule per kg. So we know specific refrigerating effect. Now to find out the specific work again, so we know the polytropic index of compression is given as 1.15. so again substituting PV into n by n minus 1 to P2 by P1 raised to power n minus 1 by n minus 1, this gives you, substituting the values, my pressure is 5.457 bar, and my specific volume is 0.0431, and substituting the n values and the discharge and suction pressures, so this is 15.735, not 157, so there is a mistake here. So 15.735 divided by 5.437, so this gives you specific work as 26.6 kilojoule per kg. So the mass flow rate I can get, so the total cooling requirement is 7.5 tons, so converting that into kilowatts is 7.5 into 3.52 or 3.5167 to be precise, and divide by my specific refrigerating effect, which is 157.7. so this gives me the total mass flow rate as 0.1673 kg per second. So the total power consumption will be my mass flow rate into specific work, which comes out to be 4.45 kilowatt. So the COP is the specific refrigerating effect divided by the specific work, which gives you 5.9. so that is a COP. Now to find out the volumetric efficiency, so volumetric efficiency is given by 1 plus C into 1 plus C into your PS by P1 raised to power 1 by n minus C into PD by P1 raised to power 1 by n minus 0.015 into R. So R is your pressure ratio. So substituting the values here. So PS is your suction pressure, P1 is your inlet, P1 saturation at evaporator. So substituting all these values, I get the volumetric efficiency is 0.8585. Then piston displacement per cylinder is half into m dot V1 by your volumetric efficiency. So it will come out to be 0.252 meter cube per minute. This will be equal to pi by 4 d square into ln. So n is 30 times your speed by L, and we get all in terms of diameter. So from this I can estimate the bore of the piston, which will come out to be 0.06 meter or 60 mm, and the length is 0.8 times the bore, so it comes out to be 48 mm. So the speed is 30 times your speed of piston divided by the length traversed. So is 30 into 3 divided by 0.048, which is 1875 rpm. As the motor is of 1400 rpm, L, D and Cm will have to be altered for say piston volume flow rate. So keeping a Cm same and D the same, one gets length as 30 into Cm by n, so length should be 64 mm. So your bore stroke by length bore diameter is 1.07 instead of 0.8, which is very high. It results in increased friction losses, so we have to reduce L. The compromise solution is to find out L as 56 mm and reduce the speed to 2.61 meters per second. So similarly, next is instead of evaporative temperature of 4 degrees Celsius, if it's reduced to -2, the process remains same. So if we follow the same process, we'll find out the specific refrigerating effect is 155.5 and specific work is 32 kilojoule per kg, and your volumetric efficiency is 0.82. So in the previous case it was 0.85, it has reduced to 0.82. So this is what we saw, increasing the pressure ratio reduces your volumetric efficiency, and m dot is 0.1312 kg per second. So capacity is 20.4 kilowatt and W dot is 4.2 kilowatt and COP is 4.86. So if you see, previously also the work done was 4.45 kilowatt, but in this case it's 4.2 kilowatt. So what happened is the mass flow rate is reduced because your suction pressure has reduced, so that caused a reduce in density and that reduced the total mass flow rate. So previously the mass flow rate was 0.1673, but in this case the mass flow rate is 0.1312. So this reduced in pressure also caused the reduce in mass flow rate, so that reduced the overall work done, even though the specific work done is more. So if your mass flow rate was same, then this work done is also higher. So that's what it means. So NCOP here is reduced to 4.86. So with that, the next question is a catalog data for a 6-cylinder refrigerant R22 compressor operating at 29 revolutions per second rotation indicate a refrigerating capacity of 96.4 kilowatt and a power requirement of 28.9 kilowatt at an evaporating temperature of 5 degrees Celsius and condensing temperature of 50 degrees Celsius. The performance data are based on 3 degrees Celsius liquid subcooling and 8 degrees Celsius superheating of the suction gas entering the compressor. The cylinder bore is 67 mm and the piston stroke is 57 mm. Compute A, the clearance volumetric efficiency. If the clearance volume is 4.8%, the actual volumetric efficiency, and C, the compression efficiency. So what's happening, we'll see, is similar. We have a 6-cylinder compressor and it is rotating at 29 rotations per second, and the capacity is given, refrigerant capacity, and total power requirement is given, and it is operating between 5 degrees Celsius and 50 degrees Celsius, and you have 3 degrees subcooling and 8 degrees superheating, and the diameter and bore and the stroke lengths are also given. So we'll see how to solve this. So the first is the state of the refrigerant leaving the evaporator and entering the compressor is 5 degrees Celsius saturation temperature and a temperature of 13 degrees Celsius. So at this state, the following properties is given. So basically your pressure is same, but it's not saturated temperature, vapor temperature, but 8 degrees more. So it's in superheated, 8 degrees superheat. So initially it is at 5 degrees saturation temperature. The corresponding pressure is 1942 kilopascal, no 584 kilopascal, corresponding to this pressure, and temperature of 13 degrees Celsius. So 5 plus 8 is 13. You will find that enthalpy is 413.1 kilojoule per kg and specific volume is 43.2 liters per kg and or into 10 power minus 3 meter cube per kg, and entropy is 1.7656 kilojoule per kg Kelvin. So if we follow an isentropic process or a reversible adiabatic process to a saturation to a saturation temperature of 50 degrees Celsius, that is pressure of 1942 kilopascal. So in that case your enthalpy is 444.5 kilojoule per kg and specific volume is 14.13 liters per kg. So enthalpy of liquid leaving the condenser and entering the evaporator is enthalpy of liquid at 47 degrees Celsius and pressure of 1942 kilopascal. So that will come out to be 259.1 kilojoule per kg. So for this case, the clearance volumetric efficiency is 100 minus 4.8, which is C, the clearance volume, which is given as 4.8%. So it is 4.8 into your pressure ratio 43.2 divided by 14.313, the specific volumes. So because PV raised to power gamma 1 by gamma, so you can write it in terms of specific volumes, minus 1, it gives you 90.1%. So we see previously the volumetric efficiency is given as pressure ratio s to power 1 by n, so that can be written as in terms of volumes. So it gives you 90.1%. So the compressor displacement rate is your 6 cylinder into your rotation, so 29 rotation per second into pi by 4 d square. So bore diameter is given as 67 mm, so 0.067 into your stroke length. So that is swept volume into number of cylinders into rotation. So that gives you 0.03497 meter cube per second or 34.97 liters per second. So the actual flow rate of refrigerant is, so 96.4 kilowatt is your work done in the compressor. So cooling capacity divide by your H3 minus H1. So condenser out minus enthalpy minus your compressor in enthalpy. It gives you 0.6260 kg per second. So the actual volumetric flow rate of the refrigerant measured at compressor suction is 0.6260 kg per second into specific volume, which is 43.2, comes out to be 27.04 liters per second. So the actual volumetric efficiency is your actual volume flow rate divided by the displacement volume 34.97 to 100, it gives you 77.3. So this is based on clearance volumetric efficiency, and this is the actual volumetric efficiency. So the compression efficiency in the isentropic work of compression is divided by the actual work of compression. So here the actual work done is your actual work for 28.9 kilowatt divided by the actual flow rate gives you 46.2 kilojoule per kg. So substituting that, so if ideal work is H2 minus H1, so compressor out minus compressor in enthalpy divided by the actual specific work of compression, it comes out to 68%. So the compressor isentropic efficiency is 68%. Moving on to next question. A single cylinder, single acting reciprocating air compressor has a cylinder of 24 centimeter diameter and a linear piston speed of 100 meters per minute. It takes in air at 100 kilopascal is 100 kilonewton per meter square and delivers at 1 megapascal. Determine the indicated power of the compressor. Assume the law of compression to be PV raised to power 1.25 equals constant. The temperature of air at inlet is 288 Kelvin. Neglect clearance effect. So P1 is 100 kilopascal and P2 is 1 megapascal. So that is 1000 kilopascal. So the diameter and piston speed is given. So P2 by P1, the pressure ratio comes out to be 10. So that is 1000 by 100. So 10. The swept volume in meter cube per minute is pi by 4 d square into L into your speed, which is rotation. The swept volume is pi by 4 into 24 by 100, that is 24, it's given as 24 centimeter, so 0.24 square into your speed is given as 30 into C by 2, which we have C by L. So converting that into minute, you will get your speed by 2. So L into rotation will give you is C by 2 in minutes. So meter cube per minute. So piston speed is 2 into L into RPM is 100 meters per minute. So this gives you 2.261 meter cube per minute as swept volume, or 2.261 by 60 meter cube per second. So this work of compression is P1 V1 into n by n minus 1 into your pressure ratio raised to power n minus 1 by n minus 1 joule per second. So where P1 is pressure in Pascal and volume of air compressed. So your work substituting here, your inlet pressure is 100 kilopascal, so 100 into 10 power 3 into your volume flow rate is specific volume. So assuming this is an ideal compressor, so there is no clearance volume here. So whatever volume is flowing is the volume swept volume. So V1 is swept volume here into n by n minus 1. So substituting n values in the pressure ratios, we'll get 11,030 joules per second, or 11.03 kilowatts. That is the indicated power of this compressor. So similar to previous, we have a single acting single stage air compressor developing indicated power of 11 kilowatt, which runs at 200 rpm and has a linear piston speed of 100 meters per minute if the suction pressure and temperature are 100 kilopascal and 15 degrees Celsius respectively, and delivery pressure is 1000 kilopascal. Calculate the dimensions of the compressor cylinder. Assume the law of compression to be PV raised to power 1.25 plus constant. Neglect clearance effects. So we know the pressure ratios here. So the outlet pressure is given. So it's just the previous problem. It's given other way. We are going to find out the compressor dimensions. So the outlet pressure is 1000 kilopascal and inlet pressure is 100 kilopascal. So with this, your pressure ratio will come out to be 10. So the process is happening as PV raised to power n raised to equals gamma. So from this we can find out the volume ratios. So V1 by V2 equals P2 by P1 raised to power 1 by n. So substituting the values, P2 by P1 is 10 and n is 1.25. So volume ratios is 6.31. So your work done in the compression cycle can be expressed in terms of pressure. It will come out to be P2 V2 plus P2 V2 minus P1 V1 by n minus 1 minus P1 V1. Or you can say n into n minus 1 into P2 V2 minus P1 V1. So substituting the values here, so dividing it by the mean effective pressure is the work done divided by the displacement volume, which is V1. So dividing it by V1, you get the mean effective pressure, and substituting the values, we get the mean effective pressure as 292.4 kilopascal, and the piston stroke is piston speed per minute divided by piston strokes per minute. This is 2 into rpm. So piston speed is 100 and piston strokes is 2 into 2000. So that gives you 0.25 meter or 25 centimeter. So that is the piston stroke length, and the indicated power is your mean effective pressure into stroke length into the area into the number of cycles per second. So indicated power is 11 kilowatt, which is given, and mean effective pressure is 292.4 into 10 power 3 into the stroke length is 0.25 into pi by 4 d square into your number of cycles per second, so 200 by 60. So from this we can find out diameter, which comes out to be root of 574.79, and which is equal to 23.98 centimeter. So that is the diameter of the piston. So 2 more problems on compressors. So first is desired to compress 16 meter cube of air per minute from 1 bar, which is 100 kilopascal and 294 Kelvin, to 10.5 bar, which is 1.05 megapascal calculate the minimum power required to drive the compressor with two-stage compression and compare it with the power required for single-stage compression. The maximum temperature in the two cases, the heat to be removed in the intercooler per minute, the amount of cooling of water required per minute if the inlet and outlet temperature of the cooling water to and from the intercooler are 15 degrees Celsius and 14 degrees Celsius. Assume the value of index of compression process to be 1.35 for both cases. Also assume proper intercooler pressure for minimum work and perfect intercooling, and R and Cp values are given. So you need to compress 16 meter cube by R, that is the volume per minute, and the pressure is given, inlet pressure, and our temperature is given, and outlet pressure is also given. We need to find out the minimum work in a two-stage compression and compare with the single-stage compression. The maximum temperature in both the cases, the heat to be removed in the intercooler, and the amount of cooling water required. So this is how the process looks. So we are assuming an ideal case. So from 1 to 2 dash is single stage, and then you are doing an intercooling to 2 dash to 2. So if 1 to this dotted line, it will be isothermal process, and then from 2 to 3 you are doing an again a compression. So we need to find out this intermediate pressure. So the final pressure to the initial pressure ratio is 10.5. So intermediate pressure, which we have seen for minimum work, is for maximum efficiency, is root of P1 by P1 into P3. So that is, or you can say the final pressure ratio raised per half will be the pressure ratio required in each stage. So it comes out to be 3.241. So your intermediate pressure is 3.241 into 10 power 5 Pascal. So each stage pressure ratio is 3.241 in two stage. So with that we can find out the total work for two stages, which is twice of, because both stages are operating with the same pressure ratio. So 2 into n minus 1 into P1 V1 multiplied by Rp raised to power n minus 1 by n minus 1. So substituting the pressures P1 and volume flow rate is 16 meter cube per minute, 16 by 60, and substituting the n values and pressure ratio, we will get the total work done for two stage compression is 73.17 kilowatt, and for if you do it in a single stage, the pressure and volume all remain same. Your pressure ratio is 10.5 instead of 3.241. So in this case your pressure is 86.25 kilowatt. And if you see the temperature, so temperature is T3 by T1 equals P3 by P1 raised to power n minus 1 by n. So if you do it in a single stage, T3 is 541 Kelvin, and T2 dash will be 398.72 Kelvin. So this will also be the T3 temperature after, because we are doing intercooling. So the amount of heat which the temperature drop which has to happen to the gas in the intercooler is, your temperature is 398.72 and it has to come to temperature of 273. So now mass of air compressed per minute is P1 V1 by RT1, which gives you a mass is 18.96 kg per minute. So heat rejected is mass into m dot Cp into T2 dash minus T2. So substituting, your heat rejected is 1.1995 kilojoule per minute. So So heat gained by cooling water in the intercooler is m dot Cp delta T. So mass of this will be equal to the heat rejected in the intercooler. So substituting that, you can find out the mass of water which is required. It will come out to be 19.06 kg per minute. So next question is, and last question, a two-stage single acting air compressor for a diesel engine runs at 250 rpm and takes in 6 meter cube of air per minute at a pressure of 1 bar and temperature of 15 degrees Celsius. It delivers the air at 70 bar and compression is carried out in each cylinder according to the law PV raised to power 1.3 equals constant. So assuming complete intercooling and mechanical efficiency of 80%, determine the minimum power required to drive the compressor. Calculate also the cylinder diameters and common stroke if the average piston speed is 170 meters per minute. Neglect effects and wire drawing losses. So we have two-stage single acting air compressor. So it is running at 250 rpm and the volume flow rate is 6 meter cube per minute and the pressure is 1 bar and 15 degrees Celsius at inlet. So it is delivering at 70 bar and its compressor is carried out in each cylinder according to law PV is per is given. We need to assume intercooling and mechanical efficiency of 80%. Determine the minimum power required to drive the compressor and we need to find out the common cylinder and diameter. The piston speed is given as 170 meters per minute. So if you see, this is how the process will look. So 1 to 2 dash is the process and then we are doing an intercooling 2 dash to 2 and then 2 to 3 there is again compression in the second stage. So for the minimum indicated power, the pressure ratio will be in each stages pressure is, so first is 70 bar from 1 bar, so root of 70 so the P3 by P1 raised to power 0.5, so that is the each stage pressure ratios, so that's why n minus 1 by 2n. So that will straight away give you each stage pressure ratios. So substituting here 2n by n minus 1 into P1 V1 raised to power Rp to Rp raised to power n minus 1 by 2n minus 1. That is the total minimum indicated power for the two stages. Substituting the values, n is 1.3, the inlet pressure is 1 bar, so 1 in 10 power 5 into your volume is 6 meter cube per minute, so 6 by 60, and the outlet pressure is 70 bar and inlet pressure is 1. So substituting you get 54.773 kilowatt. So that is the power required to drive the compressor. So here it's given as the efficiency is 80%. So the actual work which is required is the idle work divided by the mechanical efficiency of the compressor. So 54.773 divided by 0.8 gives you 68.466 kilowatt. So the minimum brake power required to drive the compressor is 68.466 kilowatt. Next is we need to find out the cylinder diameter and stroke length. So we'll find out the stroke length first. The stroke length is mean piston speed divided by number of strokes per minute. So mean piston speed is 170 per minute divided by 2 into your strokes per minute, which is running at 250 rpm. So 2 into 250, which gives you 0.34 meter or 34 centimeters. So that is the stroke length. And then using this we can find out the stroke volume, which is pi by 4 d square L into your speed. So 6 meter cube per minute is your volume flow rate. So divide by speed at 250 rpm will give you the swept volume pi by 4 d square L. So L is known, so only unknown is diameter. So from there you can get diameter as 0.0899 is the d1 square. So diameter will come out to be 0.3 meter or 30 centimeters. So for now, to have perfect intercooling, your P1 V1 equals P2 V2. So P1 into D1 square equals P2 into D2 square, assuming your lengths are same. So D2 by D1 raised to power 2 equals P1 by P2, and P2 is root of P1 by P3. So this will come out to be root of P1 by P3, and so the diameter ratio is 0.1196. So D2 by D1 will come out to be 0.346. So the high pressure cylinder diameter equals D1 is 0.346 into 0.3, the low pressure cylinder diameter. So this comes out to be 10.38 centimeter. So high pressure cylinder diameter is 10.38 centimeter. So this is assuming your temperature is constant. So that's why P1 V1 equals P2 V2, because your temperatures are constant. So your diameter for the high pressure cylinder is also low, because the specific volume will be higher at higher pressures. So they are lower at higher pressures. So with that we have found out both the cylinder diameters and also finished the numericals on compressors. So with this I have finished the reciprocating compressor parts. So this ends applied thermodynamics course. So we'll see a review session tomorrow at 5. I'll brief you what we have covered in this course and just go through in a glance on each of the topics and just a refresher on that. So we'll have a session tomorrow at 5. So with that note, I'll end the session today. Thank you.